Hello students, welcome back to JCE Connect series of lectures. So we have started the chapter Orifice and mouthpieces. So in previous classes, we have discussed about the definition of orifice, then vena contracta, then the classification of orifice. So there are different classifications based on the shape, based on the size, and based on the downstream condition or the nature of discharge, how the orifices can be classified. We have discussed in earlier class. So even also we have discussed flow through and orifice. So flow through and orifice and the theoretical velocity we have calculated, that is V equal to root of 2gh. This theoretical equation we have obtained in previous class. So this was the theoretical equation, and this equation is called as, this equation can also be called as Torricelli's equation, Torricelli's, Torricelli's equation. In this analysis, a loss of energy is not being considered. Here the energy loss we have not taken into account. And to account the loss, to account that energy loss, a coefficient that is CV, a coefficient that is a CV, that is called as a coefficient of velocity, or it is also called as a velocity coefficient, is introduced. Then the coefficient of velocity is defined as, this coefficient of velocity is defined as the ratio of actual velocity divided by theoretical velocity. The ratio of actual velocity to theoretical velocity gives coefficient of velocity. Therefore V actual, if you want to calculate V actual, it will be CV times V theoretical. So this is the formula you get, CV times V theoretical. I hope you understood this one. So this derivation we have already done in previous class, and the value of CV, which will ranges from 0.95 to 0.99. It will be between 0.95 to 0.99. So it will be 0.95 to 0.99. In general, for a sharp edged orifice, it is taken at 0.972, 0.98. Can take 0.97 to 0.98. And further, the cross-sectional area of jet at vena contracta, if you take further, so here there will be a sudden there will be energy loss. That energy loss we have taken into account by introducing a term called as a coefficient of velocity. Further, if you take at the position of vena contracta, so that is the cross-sectional area of the jet at vena contracta, that the area, if you take here, it will be a AC, is related to the orifice area. This area, whatever the area you are considering at vena contracta, if you relate the area at vena contracta to the area of orifice, then we get one more coefficient, that is called as a coefficient of contraction. So that we'll discuss again in the next part. So I hope you understood the derivation here. This is the theoretical velocity equation. So let us move to the next one. So next is hydraulic coefficients. They're very important. You can write here is these are very important points for for the examination point of view. These points are very important. Hydraulic coefficients. What are the hydraulic coefficients? So the hydraulic coefficients are the they are representing the losses, and at various stages how the losses are being considering, or how the losses are occurring, they are being termed as a hydraulic coefficients. So hydraulic coefficients are there are three types of hydraulic coefficients. They are coefficient of velocity, that is CV, coefficient of contraction, CC, and coefficient of discharge. So these three hydraulic coefficients generally we considered in case of flow through tanks. Okay, so let us define one by one. So that is coefficient of velocity, coefficient of contraction, and coefficient of discharge. So let us first define the coefficient of velocity. As I discussed earlier, that is the ratio of actual velocity to the theoretical velocity. That is, it is defined as the ratio between the actual velocity of a jet of liquid at vena contracta and the theoretical velocity of jet. It is denoted by a symbol CV, and mathematically the CV is given as, you can write the CV value as, CV will be actual velocity, that is the ratio of actual velocity of jet at vena contracta divided by theoretical velocity. Then the actual velocity you can write as a V, theoretical velocity as root of 2gh. V is the actual velocity and root of 2gh is the theoretical velocity. If you want to write the actual velocity V, the V will be what? CV times the theoretical velocity. And generally, as I said, the CV value varies from 0.95 to 0.99 for different orifices, depending on the shape, size of the orifice, and the head under which the flow takes place. Generally, the value of CV to be taken as a 0.98 is taken for the sharp edged orifices. And remember, the CV value generally it will be a 0.98. So in problem, if not given, just you take it as a 0.98. Even you can calculate this value in a laboratory through the experiment. Okay. Next, the coefficient of contraction. Coefficient of contraction means it is defined as the ratio of area of jet at vena contracta divided by area of orifice. It is denoted by a symbol CC. You can write, let A represent the area of orifice and AC represent the area of the jet at vena contracta. Then the CC can be written as the ratio between area of jet at vena contracta to area of orifice. So area of jet at vena contracta can be written as AC and area of orifice as A. And the value of CC varies from 0.61 to 0.69 depending on the shape and size of the orifice and head of liquid under which the flow takes place. In general, the value of CC may be taken as 0.64. The next one is the coefficient of discharge. It is defined as the ratio of the actual discharge from an orifice to the theoretical discharge from the orifice. It is denoted by a symbol CD, and if Q is the actual discharge and QTH is the theoretical discharge, then mathematically the CD is given as, CD will be Q by Q theoretical, that is actual velocity into actual area, that is A into V. You can write as A into V, that is actual velocity, since the numerator represents the actual discharge. So you have to write A into V, that is actual velocity divided by actual velocity into actual area, then divided by theoretical velocity into theoretical area. Then actual velocity by theoretical velocity will be CV, then actual area by theoretical area will be CC. Then the CD will be what? CV into CC. Then the value of CD varies from 6.61 to 0.65. For general purpose, the value of CD is taken as 0.62. Okay, so these are some 3 hydraulic coefficients. Even one more hydraulic coefficient is there, that is coefficient of resistance. So coefficient of resistance, that is CR, that is coefficient of resistance, that is CR. Just a minute. Coefficient of resistance CR, that will be defined as the ratio of kinetic energy as the liquid flows through the orifice to the kinetic energy possessed by the liquid. So the ratio between the kinetic energy of the liquid flows through the orifice to the kinetic energy possessed by the liquid. Since the value of coefficient of resistance is very negligible, hence it can be neglected many times. Okay, so this is one more coefficient, that is coefficient of resistance. Coefficient of resistance. Okay, now let us take again a sharp edged orifice. It's a orifice, it's nothing but opening only. The edges are sharp here. Just look at the edges here, it is made very sharp. Then the Q will be what? CD into A into root of 2GH. Value varies from 0.6 to 0.7. And bell mouthed orifice, that is Q equal to CD into A into root of 2GH. So here, look at here. This is called a bell mouth. The mouth will be this, the entrance will be like a bell. So hence it is called as a bell mouthed orifice. Again, as we know, the Q equal to what? A into V. Q equal to A into V. Then we can write the area of the orifice into velocity. Then if you consider the loss also into account, that is CD to be introduced, then we get the actual discharge. CD into A into root of 2J. This A into V, this will be A into VQ. If we introduce a term CD, then we get the actual discharge. Bell mouthed orifice also with the same formula to be used. It is also 0.6 to 0.7. Here a small rectangular orifice. So again, when the available head of the liquid is more than 5 times the height of the orifice, available liquid head means H is more than the 5 times the height of the orifice, means this height of the orifice. So the H is more than 5 times D, then it is called as a small orifice. Again, the formula is this one. If available head of the liquid is less than the 5 times, if head is less than 5 times of D, then the orifice is called as a large orifice. So for a large orifice, if you take like 2 different heads, H1 and H2, so it can be taken as like this. This formula to be remembered: 2/3 of CD into B, root of 2G into H2 raised to 3 by 2 minus H1 raised to 3 by 2. Okay, just to remember the formula for the large rectangular orifice if there are 2 heads. Okay, then small circular orifice. Small circular orifice, when the available head of the liquid is more than 5 times the diameter of the orifice, is called as a small circular orifice. This is a formula to be used for the calculation of discharge. Then the large circular orifice, when the available head of the liquid is less than 5 times the diameter of the orifice, is called as a large circular orifice. So this is the formula, that is 0.992 is introduced, and this is the formula to be used: CD into pi by 4 D square into root of 2GH. Okay, for the large circular orifice. Then fully submerged orifice, it means if the outlet side of an orifice, see if you take the outlet side of the orifice, this is the outlet side of the orifice on the downstream side. If the outlet side of the orifice is submerged under liquid, it means it has this orifice completely submerged under this liquid. If you take this one, you completely submerged under this liquid, it is called fully submerged orifice, where H1 represents height of the liquid on upstream side, H2 represents height of the liquid on the downstream side. H2 represents height of the liquid on the downstream side. Then the Q will be what? CD into a root of 2G into bracket H1 minus H2. That is Q. Partially submerged orifice. If the outlet side of an orifice is only partly submerged, if the outlet side of the orifice, if you take, if it is only partially submerged under liquid, is called partially submerged orifice. See, if this is partially, means it's not completely submerged, the level of the liquid on the downstream side tank is here. The orifice is here, it has partially submerged in this tank, hence it is called as a partially submerged orifice. If the outlet side of an orifice is only partly submerged under liquid, is called partially submerged orifice, where H represents the difference between the liquid surface, means this H, this is H1 minus H2, that is height of the liquid on the upstream side, then height of the liquid on the downstream side. Then the formula, if you apply, this will be the formula to be used to calculate the discharge for the partially submerged orifice. Okay, two different formulas to be applied. 2/3 of CD1 B into root of 2G H raised to 3 by 2 minus H2 raised to 3 by 2 plus CD2 B into bracket H1 minus H root of 2GH. Okay. So next is mouthpiece. So regarding a mouthpiece, I'll discuss in the next part of the video.